All right, let's talk about one of the biggest problems in all of robotics. How do you build a machine that can move around our messy, cluttered, unpredictable world without, crashing into everything? Well, today, we're opening up the Roboticist toolkit to see exactly how they do it. It all boils down to one simple, crucial question. Right? This is it. I mean, think about it. From a Roomba trying not to run over your cat, all the way to a rover navigating craters on Mars, every single one of them has to solve this problem. And the solutions, they're really clever, surprisingly elegant, and honestly, pretty intuitive once you see how they work. So our first tool is basically a brilliant bit of mathematical judo. Before a robot can even think about moving, it has to simplify the world around it, which is just way too complex. And it does this with something that sounds simple, but is incredibly powerful: the point robot trick. Okay, so the core idea here is all about a clever transformation. On the left, you've got the real world, what roboticists call the workspace. Trying to calculate collisions for a big, clunky robot arm in this space is a complete nightmare. So they use a secret weapon, which you see on the right, the configuration space, or C-space for short. The trick is, instead of tracking the robot's physical body, we just track its configuration, its joint angles, and we represent that entire robot as one single tiny point on a brand new map. And this visual just shows you how powerful that is. Look at the top image. That's a physical robot arm trying to find a path between those two boxes. It's complicated. But now, follow the arrow down. In the C-space, the entire arm is now just that little dot, and the boxes have become these weird expanded red no-go zones. Suddenly, the really hard problem of moving a 3D arm becomes the much simpler problem of just drawing a line for a point from start to goal. It's a total game changer. And this is where it gets really, really cool. Look at that arm on the left. It's got two joints, right, a shoulder and an elbow, and each one can spin 360 degrees. Well, what's a 360-degree rotation? It's just a circle. So what shape do you get when you combine the space of all possible shoulder circles with all possible elbow circles? You get the shape on the right, a torus, also known as a donut. So the robot's entire posture, its complete configuration, can be represented as a single point P somewhere on the surface of that donut. Isn't that wild? Okay, so let's see what happens to an obstacle. On the left, you've got our physical arm and a simple red sphere it needs to avoid. But when you translate that to our C-space on the right, which is really just a chart of shoulder angle versus elbow angle, that simple little sphere becomes this strange, warped red shape. But here's the key. Who cares what the shape looks like? The computer doesn't care. It just sees a 2D grid and knows its job is to find a path for our little point robot from start to goal without going into the red area. The hard 3D problem is now a simple 2D one. Okay, so C-space gives us the map. That's huge. But a map doesn't actually tell you how to move, right? For that, we need an engine, and our next tool gives us just that. It's a method inspired by physics called potential fields, and it uses virtual forces to literally push and pull the robot through its world. Now, I know the name potential fields sounds a little intimidating, maybe a bit technical, but trust me, the intuition behind it is super simple. We're going to use three things that we all understand: a bowl, some magnets, and a spring, to build up a really clear picture of how a robot can kind of feel its way to a goal. First up is the bowl. So I want you to imagine that the entire map is a landscape, like a big rolling hill. We're going to say that the goal is the lowest point in this whole landscape. It's the very bottom of a big bowl. Now, if our robot is a ball and we place it anywhere on the side of that bowl, what's it going to do? It's going to naturally roll downhill right to the goal. This creates a kind of global attractive force that's always pulling the robot in the right general direction. But that's not enough, so we're going to add two more forces. First, on the left, imagine every obstacle is like a super powerful magnet, and it's got the same charge as the robot, so it creates this repulsive force that pushes the robot away. Then, on the right, imagine there's a spring or a rubber band that's always connecting the robot to the goal, constantly pulling it forward. It's the combination of this push from the obstacles and this pull towards the goal that creates really smart fluid navigation. So let's peek under the hood at the math that makes this virtual rubber band work. This is the formula for the attractive potential, U@. Don't let it scare you. Every part has a simple job. The D here is just the distance to the goal. Now, the really important part is that it's squared, D squared. What that means is that the pulling force isn't constant. It gets much, much stronger the farther away the robot gets, just like stretching a real rubber band. And that little Greek letter, zeta, that's just a strength knob that the programmer can turn up or down to decide exactly how strong that pull should be. And now for that protective bubble that pushes the robot away from danger. This formula is what creates it, and the real magic is right here in this one little term, 1 divided by d, the distance to the obstacle. Just think about it for a second. What happens when the robot gets really, really close to hitting something? That distance, d, becomes a tiny, tiny number, right? Almost 0. And what happens when you divide by a tiny number? The result just skyrockets towards infinity. And that is the elegant mathematical trick that creates an infinitely strong force field, a virtual wall the robot can never cross. It guarantees it won't collide. And here is how it all comes together beautifully. We just add those attractive and repulsive forces to create one single energy landscape. The obstacles become these high-energy hills, and the goal becomes this low-energy valley. The robot's job is now incredibly simple. Just always move downhill. In math terms, we say it follows the negative gradient, which is just a fancy way of saying it finds the steepest downhill path from wherever it's standing and takes a little step in that direction. But this method isn't perfect. It has one major fatal flaw, and it's called a local minimum. Just imagine the robot is in a little ditch, and the real goal is on the other side of a big hill. The pull forward from the goal can be perfectly canceled out by the pushback from the hill, and so the robot gets trapped in this little valley that isn't the true goal. It just gets stuck. So what happens if the robot has no map at all? What if you just drop it into a totally unknown room and say, go? For that, you need a tool for improvising. And that's where the bug algorithms come in. They're a set of really simple rules for navigating when you're basically flying blind. Let's look at the first one. It's called Bug 1, and it's very cautious. As you can see from the steps, it starts by heading straight for the goal. Simple enough. But when it hits something, it doesn't try to be clever. It patiently follows the obstacle's entire boundary all the way around, and all the while it's memorizing which single point on that perimeter gets it closest to its final destination. Once it's made the full loop, it travels back to that single best spot, and only then does it leave and continue on its way. It's safe, but yeah, it's not very efficient. And you can see that logic playing out right here. The blue robot starts off, bumps into the red obstacle, and then begins its full exploration loop. As it traces that whole perimeter, it's constantly calculating, okay, where's the best spot to leave from? Once it has completed the whole loop, and it knows for sure what that optimal leave point is, it travels back there, and then makes a beeline for the green flag. The cool thing is, this method guarantees it'll find a path if one actually exists. Okay, so we've got tools for a known map, and we have tools for an unknown map. But so far, all of our obstacles have been sitting still. For the final level of this explainer, we need a tool to handle the ultimate robotics challenge, a world where the obstacles are moving too. Now, to handle moving obstacles, we have to make a big mental shift. The key insight is we have to stop thinking about avoiding forbidden places and start thinking about avoiding forbidden velocities. This red cone you see here is called a velocity obstacle. And what it represents is every single possible velocity Robot A could choose that would result in a crash later on. So as long as Robot A picks a new velocity for itself that is anywhere outside of that red cone, in the green safe zone, it is guaranteed to avoid a collision. But there's a problem with that basic approach, which you see on the left. If two smart robots are using it, they can get into this weird dance of indecision, kind of shaking back and forth because each one is expecting the other one to do all the work of getting out of the way. The solution on the right is something called the reciprocal velocity obstacle, or RVO. With RVO, each robot makes a simple assumption. The other robot is just as smart as me, so it's going to do half the work to avoid a crash. And this simple idea of cooperation is what allows for that smooth, natural-looking movement even in really dense crowds. So there you have it. That's the core of the roboticist's toolkit. We started with C-space to turn a hard problem into an easy one. Then we used potential fields to generate motion, almost like a ball rolling downhill. We gave our robot bug algorithms so it could explore unknown places. And finally, we leveled up to velocity obstacles to handle a world that's always in motion. Each tool is like a new skill for the robot to learn. And as this quote from our source material really drives home, this stuff isn't just one thing. It's this beautiful, rich field where you have geometry to understand space, physics to model forces, and real practical software engineering to actually make it all work. And that kind of leaves us with a final, bigger thought. That jump from the basic velocity obstacle to the reciprocal one was all about adding a simple rule of cooperation. As these robots start moving out of factories and into our homes and onto our streets, how will these underlying principles, ideas like shared responsibility and predictive movement, how will they change not just the robot's code, but maybe how we interact with them, and even how we interact with each other? Thanks for watching.